Here we're interested in looking at a adiabatic reversible process for an ideal gas. So we start at pressure P1 and T1, and then, for example, here we're showing adiabatic compression to pressure P2 and T2. So the typical question is, we know pressure 1 and temperature 1. If we know pressure 2, how do we determine temperature 2? Well, in another screencast, we show that if we have a constant heat capacity, Cp, then temperature 2 over temperature 1 is related to pressure 2 over pressure 1 raised to R over Cp. So the question is, if we don't have a constant heat capacity, then what is the appropriate equation? To determine that, we have to go back to look at how we derive this equation, namely delta S equals 0. We show that's related to two terms that resulted from applying the first law to reversible process, and then delta S has the integral dq reversible over T. And so I'm going to rearrange this equation. So let me pause. So I've integrated the second term. R is a constant, the gas constant. And then I'm going to make a substitution, ideal gas law. So let me pause again and do that. So this is just applying the ideal gas law for V2 and for V1, and the R term cancels. I'm going to separate this second term into two terms, see why that's useful. And what I've done is, if we have the log of A times B, that's equal to log of A plus the log of B. And then I flip the P1 over P2 to P2 over P1, and that results in a negative sign here. And so now I'm going to rearrange again. So I brought the log of P2 over P1 to the left side, and I've rewritten the term for the log of P2 over P1 in terms of the integral. So if I integrate d2 over t, I get the log of t2 over t1. And the reason I do that is because now I can combine these two terms and write Cv plus R is equal to Cp. So I have integral Cp, and now Cp is not a constant. We have to write Cp in terms of some expression in terms of temperature. And the normal term, let me pause again. So I've written Cp in terms of the constants A, B, C, and D, which of course depend on which molecule we're interested in, and the polynomial expansion in temperature. And now we can integrate each of these terms. So let me rearrange it, divide through by t before we do that integration. And we can then integrate the right side and substitute in the limits. So the first term is the constant A. Second term is T2 minus T1. Third, C over 2, as we do the integration, T2 squared minus T1 squared. And then the last term on the right side is D over 3. I'm integrating dt squared, so we have T2 cubed minus T1 cubed. So what we have now is an equation that relates initial and final pressure to initial and final temperature, ideal gas, adiabatic reversible process. And so to solve this, because it's nonlinear, we're going to just use something like Solver in Excel. But this is the equation then that we're going to use instead of the simplified equation that we have up here for a constant heat capacity. Now, the thing to note that's important is we derive this equation for a closed system, but it applies just as well to a flow system at steady state, where we have state functions. And so the fact that we only have an equation in terms of state functions it means it's independent of how we get to these conditions for adiabatic reversible process.